So far, we have tested a single population parameter. Could have been a mean, more generically as mu, or as a proportion p. We have tested a population parameter for variance, and each of those applications also had confidence interval formulas that we looked at. We had central limit theorem applying when we had large samples. When we had small samples, if we sacrificed the large sample condition, then we had to pick up an additional condition of normality. So everything so far has just been inference or estimation about a single population. Okay, now we want to expand that. Suppose we're looking at two population means, and you wish to compare two population means for equality, or do they differ by some specified amount? All right, we can do this in a couple of different ways. Here we're going to talk about dependent samples. So the examples of dependent samples is also referred to as paired data or paired samples. So before and after data. If you take a subject, you measure it before treatment, you measure it after treatment. Okay, those data are paired. Okay, panelist evaluations. So in some of the experimental foods in meat science and things they do, there are a lot of panelist studies, and so that is you give each panelist two products to evaluate, and they're each scored. That panelist influences both samples, right? So that makes it paired. Okay. There's other studies we see information collected on identical twins, because genetically, they're looking at genetic studies and that. So we know that they are identical twins are genetically identical, or close to, I suppose, for all practical purposes. Okay, so we. How do we adjust for the fact that these data are paired, or that the samples are not independent of each other? Okay. Can I still test means? Can I still test variance and that sort of thing? All right. So our notation here, we have our two groups of dependent samples. And of course, if they're paired, then both samples have to have the same number in it. So I'm not interested then in total number of observations, but the number of paired observations. I'm going to compute a difference across sample 1 to sample 2 for each pair, okay, in the data set. Okay, I can compute the average difference that we observe, and we call this D bar. Some textbooks may use an uppercase D. So the average difference, so the DI then is the difference between group 1 and group 2, and then average all those differences up. So these values for DI can be positive or negative. Okay, even if your original data is all positive, okay, or all negative, whatever. So DIs can be either one. Okay, the standard deviation of D, the differences. So this is just our standard deviation formula that we had back in the dispersion lecture, one of the very first lectures we had. This is exactly the same formula we had, except then we had Y sub I and Y bar, and now it's D and D bar, right? I'm not doing anything differently than we did before. Okay, so we want the standard deviation of those differences. Mu1 and mu2 denote the populations 1 and 2 means respectively. Okay, we're interested in testing hypotheses or estimating the difference between these two means. All right, so just kind of overview how this works. So we have n different pairs. All right, we collect our sample 1. We measure, say, a set of x's on all of these pairs. We measure all of our y's, y1, y2, all the way down through yn. Okay, the difference on those, so we compute our first difference, and we take x1 minus y1. All right, sample 2, x2 minus, observation 2, x2 minus y2, all the way down to the last one. Our nth difference would be x sub n minus y sub n. Now, it doesn't matter that you take x first, x minus y, or y minus x. Whatever you do, be consistent and do that for everybody. All right, so if you're always taking the difference of sample 1 minus sample 2, just make sure you do that for all the differences. Don't take the absolute value of the differences. The differences are what they are. Okay? Then down here at the bottom, you can collect summary information. We could end up with sum of the x's, we could have the sum of the y's. All right. Over here we'd have the sum of the di's, and if we wanted to look at, we could also measure d bar. It would be sum of the di's over the number of pairs, lowercase n. We could also compute s sub d. Okay, and that means we'd need the sum of the squared d's, or we could use these two pieces of information in one of the computational formulas or the stat functions in our calculator. Okay, so this value d bar estimates the true population difference between the means mu1 and mu2 in the same way that y1 bar estimates mu in a single population and single sample case, right? Okay, here this value of d bar measures the true difference between the two population means. If our populations 1 and 2 are normal, then so are all the differences di. So that means that the di's would be normally distributed. If pop 1 and pop 2 are normal, and I'm computing group 1 minus group 2, then that means the mean is going to be mu1 minus mu2. And the variance is going to be sigma squared with subscript d. And so our s sub d value, if we square that, it's going to approximate sigma squared d. All right. So now our hypothesis test questions. Same format. All right, here I have the difference, mu1 minus mu2 equals delta naught. Delta naught is some specified value. Okay, we can look at a two-sided test, a right side test, a left side test. Most typically delta naught is 0. You want to know if mean 1 is equal to mean 2, or is mean 1 greater than mean 2, or mean 2 greater than mean 1. Okay, so most typically delta naught is 0, but it does not have to be. All right, our test statistic is the same in all three cases. Now notice what happened here. Plain English interpretation. Estimate minus hypothesized value divided by the standard error of the estimator. So this denominator is S with subscript d bar, standard error of the difference, average difference, right? Okay, so this is exactly the same form of the t statistic that we did for single population tests about mean with a small sample, right? There we had y bar minus mu naught over the standard error of y bar. We have the same thing here, except now it's d bar. Okay, so by computing all the differences across the pair, we took these two samples, computed the difference, and made it a one sample test. By computing the differences, we've removed the effect of that panelist who's evaluating both products. Because if a panelist evaluates both products, then we assume they're going to have the same preferences or biases as they evaluate that. And so when I take this difference, that subtracts out. Okay? Two-sided test, two-sided rejection region. It's a t statistic. So, like I said, we took this two-sample problem. By computing the difference, we made it a one-sample problem. And so all this follows the same thought process as the one-sample test did before. Right-hand test, right-hand rejection region, left-side test, left-side rejection region. Right? Again, does this seem repetitive? All right? That's good when it does. Okay, so what we're looking at is that we have random samples, but they are dependent. If they weren't dependent, then I wouldn't be subtracting the two things. It wouldn't make sense to. Okay, what do I do if they're not dependent? Come back for another lecture. Okay, we'll do that in our next lecture. All right, but if they're dependent, then we just subtract across the pair. Okay, we're saying that these differences are normally distributed. By having that normal distribution, then we can use the t distribution to analyze things. Okay, for this application, it's sample size minus 1 for the degrees of freedom. That matches what we did before, number of where we had only a one sample test about a mean. It was sample size minus 1. Here the sample size is number of pairs because you've taken the difference. All right? No surprises? Okay, good. What do you suppose the confidence interval formula is? Again, the plain speak for the interval is the estimate plus or minus a critical value times the standard error of the estimate. Okay, I said the same thing in the last 2 lectures what we did with the mean. Okay, random samples, these are the same thing, conditions or assumptions we had on the test. We could also talk about one-sided intervals or confidence upper bounds and confidence lower bounds to correspond with the one-sided tests. They're just not listed here. All right, we have a couple of examples. A study is undertaken to determine how consumers react to energy conservation efforts. A random group of 60 families is chosen. Their consumption of electricity is monitored in a period before and a period after the families are offered certain discounts to reduce their energy consumption. Both periods are the same length. The difference in electricity consumption between the period before and the period after the offer is recorded for each family. The average difference in consumption and the standard deviation of the difference are computed. The results are that D bar is 0.2 kilowatts, that's taken before minus after, and the standard deviation of those differences is 1. At alpha equals 0.01, is there evidence to conclude that the conservation efforts reduce consumption? All right, so someone's gone through, we don't have the raw data, okay? We'd have to have the sample 1, sample 2, and compute the differences if we began with raw data. Okay, so here somebody's done quite a bit of work for us already. So is there evidence to conclude that the conservation efforts reduce consumption? All right, so what would we write for our research question or our hypotheses? Well, here, directional wording, right? Reduce. In my mind, when I hear reduce, I think left side test. Not necessarily the case, though, when you have to. Whether this is a right-hand test or a left-hand test depends on how I computed the differences. Okay? I did before minus after, or was given before minus after. And so if there is a reduction, before minus after should be what? Positive or negative? Okay, if there's a reduction, before minus after should be positive. Okay, so my question then, research question, really is the before, which I'm going to indicate with the B, is before greater than after. That's really the question as it's being asked to me, isn't it? Is there a reduction? Is after smaller than before? Okay, so that translates to there is a reduction. That is not the form that I was given in the table for hypotheses, but that's how the question was asked to me. So that's what I usually like to write out, how's the question appear in the problem? What does that directly imply? And then write it then as the formula's set up. Okay, so that would mean that the null hypothesis is what? There's no reduction, or in fact it went the other way. So this would say that before is less than or equal to after. No reduction. Okay, so this, this went before minus after, so I want to make sure I write this as before minus after. All right, so that I would subtract after from both sides. So before minus after is strictly greater than 0. Okay, my delta naught is 0. We're conducting our test at the 0.01 level. And let's see, we need to recover some information here. Our average reduction, 0.2 kilowatts. And our standard deviation of all those is 1. And we did this based on 60 pairs, right? Now, even though n is 60, so just stay on the t-tables, and because you know t approaches standard normal, so we'll just stay on the t-tables. Okay. So this is what we have right here. Agreed? Okay, so our test statistic we're going to compute t, and this is equal to, our d bar is 0.2. The hypothesized value is 0, divided by standard deviation 1 over the square root of 60, the number of pairs, or number of families here. When we compute this, we get what? I have 1.5492. We're going to reject the null hypothesis if what happens? If t is large, if t is greater than or equal to a t determined by what? Right-hand area, 0.01, and how many degrees of freedom? 59. Now with this textbook, if we go to the table, there is no 59 degrees of freedom. Okay? I'll just go over to the 0.01 column. Oops. All right, so go to the 0.01 column when we have 50, 55, 60. All right, by the time I zoom, the column headers will go off. Where'd my straight edge go? All right, so in the 0.01 column, just the values here, 2.4033, 2.3961, 2.39, we're tumbling. There we go. 2.4033 associated with 50 degrees of freedom, 2.3961 with 55, 2.3901, all in this column here. They're all very close together. What do you suppose happens if we put in 51 through 54 and 56 through 59? You're seeing changes in the third and fourth decimal place only. All right, so the tables then become less complete as the degrees of freedom increase because the differences between these critical values are so subtle. Okay, so what do? All right, if we're looking at the book and we're going to use the book only, what I want you to do is like, well, there is no 59. Typically use the smaller degrees of freedom, the next smaller one, which in our case would be 55. Okay, or if you use 60. So I'm either okay with either one of those. If it makes a difference in your conclusion, in practice we would have we'd be computing p-values and looking at something using software. All right, so I'm less worried about that. But I don't want you to pick something that's not close to it. Does that make sense? So either you could choose 59 or 60. If you use don't interpolate. Just don't invest time in doing that. Okay, some instructors tell you to interpolate on those. I'm not one of them. I've told you the 2 or 3 cases we have out of standard normal where I let you interpolate, and that's it. Okay, if it makes a difference in what we're going to do, handheld calculators and software can fix the problem for us. I just need to know you understand the concept. Okay, so when you're between two values there, I don't care if you use 55, I don't care if you use 60, just whatever you use, tell me what you're doing. All right, and so that's the way I'll do it here. So which one do we want to use? Pick one, and that's what we'll do. Okay, so we're going to approximate this. Since I don't have 59 degrees of freedom, I'm going to approximate this with a T of 0.01, and then do we want to use 55 degrees of freedom or 60? You choose. Okay, so if you approximate, just tell me what you approximate with. All right, if you chose 70, if you chose 40, those would not be good approximations, and I'll get you a couple of points on that. Okay, choose 55 and 60 are the only legitimate ones to put in there, but do not invest time in interpolating. Hopefully I've beat that drum loudly enough. Okay, so the critical value then for 0.01 right-hand area and 60 degrees of freedom, that critical value from the table is what? Yeah, 2.3901. Let's try to write the 3 first. What's our decision? All right. In the cookbook approach, we're do not reject. In plain English, what does that mean?
There's no evidence.
Okay. So the evidence does not indicate a significant reduction. In energy consumption. We conducted our test at the 0.01 level. We calculated a T with 59 degrees of freedom of 1.5492. We used 60 for our critical value. Stay on the row for 60 and find the p-value. I have that the p-value is between 0.05 and 0.1. Do you agree? Or do we need to double that? We don't double because it was a one-sided test. Again, when you write your conclusion, it needs to be in the language of the problem. Also, my wording indicated that I did a one-sided test when I talk about the significant reduction here, doesn't it? Okay, and with the exception of what's in the parenthesis, this sentence makes sense to anyone who has not had a statistics class, right? That's really your goal. Anyone who has a statistics class would look at that p-value and go, I know what they're talking about. So now when you look at journal articles, you go, oh, that's what those little p-values are when I'm reading journal articles, right? That's indeed what they are. All right, Mazda RX and Nissan Z are to be compared. That's a series of cars. Or I'm not sure what generation of RX we're up to now, but okay. A random sample of 40 drivers is selected. Each driver test driving one of each model. The time of each test drive is recorded for each driver and model, and the results are given by D bar is equal to 5 seconds when I measure Mazda minus Nissan, and the standard deviation of those differences is 2.3. Compute a 99% confidence interval for Mazda minus Nissan. Okay. Why is this dependent? Okay. What about the drivers? Each driver drives one of each type of car. Okay, so that driver has an influence on both samples. So if I take the, now is there, assuming we all drive here, maybe we don't, but for those of you that do, would you believe there to be an effect due to driver? Think about it on terms of fuel efficiency and things like that, just in general, not necessarily here. Sure, drivers, there are different levels of aggressiveness, can affect fuel efficiency and can affect speeds and all kinds of things. All right, so yeah, I believe there could be a driver effect. And so that those kinds of things, I assume the person's going to drive each car the same way. So if I want to remove that driver influence, then I have to subtract across the pair, right? So I get a measure then of truly what the drivers did, or how the cars compare, and not how the drivers influence that. Okay. How would I remove that dependence? What would I have done differently to make this such that the samples were not dependent? We'll talk about how to analyze independent, but how would I have done this in order to have independent samples? Different drivers for each model. Okay, so that all the drivers for Mazdas are not the same drivers as for Nissan. Okay, so I could have done that. Okay, so what makes them paired is that each driver drives one of each car, and in practice, you would have each driver, they wouldn't always drive Mazda first, Nissan second, or Nissan first, Mazda. You'd randomize, so that way there isn't, Mazda first for some drivers, Nissan first for other drivers. Okay, all right. So we want to compute the 99% confidence interval for Mazda minus Nissan. We'll answer the question here in just a little second. So what we have is 1 minus alpha is equal to 0.99. That means alpha is equal to 0.01. We have d bar is 5 seconds. The standard deviation, again, be attentive to whether you're given standard deviation or variance. That person that writes your test may switch that up on you. Okay. We have 2.3 for standard deviation and 40 pairs. Okay. So our 99% confidence interval for Mazda minus Nissan, those means. Then I would take the point estimate. D bar estimates this difference. So we take our estimate, 5.0 seconds, plus or minus a critical T determined by what? Alpha over 2 would be 0.005. And how many degrees of freedom? (39 degrees of freedom. We're multiplying this value of t by 2.3 over the square root of 40. What do we do next? Do we have 39 degrees of freedom on the table? No? Which one? So what can you use? You can use 35 or 40. You tell me which one you're using. We're going to approximate it with what? Use 40? Okay. And that critical value is what? 2.7045. Does everyone agree? So I have 5 plus or minus. .9835. So on the left I have 4.0165. On the right, 5.9835. Everyone agree? Okay, the blank page there. Following is for the following discussion. Is 0 a likely value? Of the difference mu m minus mu n. Is 0 likely? No. This interval does not contain 0. Okay? In general, if 0 is in the interval, what would we conclude? If 0 were in the interval, then we would conclude that mu m and mu n are equal to each other, wouldn't we? 0 is the likely estimate of the difference, so therefore we cannot conclude they are different. All right? If 0 is not in the interval, then we would conclude that the means are indeed different from each other. Okay? So we know they're different. Agreed? Now let's answer our question up here at the top. Can you conclude which model has the faster mean performance time? Be careful. All right? This interval does not contain 0. This interval is entirely positive. So what does that tell me about the two means? They're different. If they're different, then one is bigger. Which one's bigger? Okay? So we would conclude that Mazda is bigger. So since we have that Mazda minus Nissan is greater than 0, all right? The Mazda mean is larger. Which car is faster? You got to vote for one for each. Which one's faster? What was our response? Number of seconds to complete some course, right? If a high performance time is a good score, I would win every race I ran. A low score is a good score, isn't it? High scores aren't always the best thing. Here, a low score is a good score. So which one is faster? Nissan. Okay, when we looked at that question, we kind of read which mean is larger, didn't say that though. It says which is faster, and the connotation with faster means was the lower mean. What would have happened differently in this problem if D bar were Nissan minus Mazda? What would be different? If this were done as Nissan minus Mazda, D bar would be -5. If it were done Nissan minus Mazda, what would the standard deviation be? Stays 2.3. Standard deviation is positive always. Okay? What would happen to our confidence interval? It would go from -5.98 up to -4.01. They have negatives and they would switch direction. Would Nissan still be faster? Yes. So like the hypothesis testing, whether it was a right-hand test or a left-hand test, depends on which way we compute our differences. That's also, how do we interpret this? If this interval is entirely positive or entirely negative, what does that mean? Okay.